Going over the notes for 5.2. We first started by defining a polynomial. A polynomial is just a monomial, which means one term, or the sum of many terms. Most of the things that we've ever worked with are technically called polynomials. A linear function like y equals mx plus b would be a polynomial. Our quadratic functions from chapter 4 would also be types of polynomials. If you have something bigger than an exponent of 1 or 2, what you want to do is put it in what's called standard form. And standard form is when you write it simply from biggest exponent down to smallest. So notice we have f of x equals this really big polynomial, lots of different terms. If we write it in decreasing order, that's the definition for standard form. The biggest exponent started as 6. So what we did from there is we just counted down. We had a fifth, a fourth, a third, a squared, an x to the first technically, and then the constant. That's what's called standard form. Now the degree of a polynomial is just the value of the biggest exponent. So in this case, the degree is 6 because that first exponent is 6. The leading term versus the leading coefficient. The term includes everything, so it's whatever is kind of that whole thing that's written first, 5x to the 6th power. The leading coefficient, though, is just the number out in front. And we use the lead coefficient and the degree to help us sketch graphs later in this lesson. And then we talked about other types of terms. A quadratic term is any term in the polynomial where you have an exponent with your variable of 2. So in this case, 4x squared is the quadratic term because it has x squared in it. A linear term would be technically anything with an exponent of 1, and that gave us negative 2x when we looked up at the list of terms in the polynomial. A constant, which we're going to use to help us find the y-intercept, is just always whatever would be left over if we plugged in 0 for all of our x's. So in this case, our constant is 1. So those are kind of just some of the key features that we looked at when defining a polynomial. So we did a couple of examples writing a polynomial in standard form if it's defined as a polynomial. The two things that we look for are whole number exponents, so exponents that are greater than or equal to 0. In that first example, we had an exponent of negative 1. So that's still a type of function, it's just not classified as a polynomial function. And if it's not a polynomial function, we don't have to do the rest of the steps. In the second example, p of x, we notice that all the exponents are whole numbers and all of the coefficients are kind of real numbers. Like there's no imaginary coefficients, which is kind of rare to have that. So that second part really isn't a huge issue. We wrote it in standard form by putting x to the 5th first because that was the biggest exponent, and then went decreasing from there until we got to the constant. The degree would be 5 because that's the biggest exponent, and the leading coefficient was negative 12. Notice for this one, we didn't have a quadratic term, and sometimes that happens. To evaluate polynomials just means for a given input of x, what's your output for the equation? And then we can do that in two different ways. First, by direct substitution. And that's what you're normally used to doing, just plugging in your variable or the value for your variable and then simplifying. And then noticing on your calculator, if you want to take an exponent like 3 to the 4th power, you should have a little arrow up key that would help you do that. And the key thing for direct substitution is make sure that you put the number for x in parentheses. That will save you a lot of extra work, especially if x is negative. The second type of substitution is new, and this is called synthetic substitution. In synthetic substitution, we don't plug in our x variable, but we use coefficients and kind of manipulate them with a pattern to get an end result. Now, to use synthetic substitution, we have to make sure all terms are represented in the polynomial. So when you write your degree and then you go in decreasing order, if any exponent term is missing, we have to use 0 as a placeholder. So here's how it works. It says use synthetic substitution to evaluate the polynomial function for the given value of x. Notice this is the same equation that we just had on the last page, and we're plugging in the same number for x. So what we do is we put that number over on the left-hand side. Also notice we had x to the fourth and x to the third, but we were missing an x squared term in that polynomial function. So I put a placeholder of 0 and kind of rewrote it in order from biggest to smallest. Then I took all the coefficients. The 2, I wrote that first. The -5. I need that 0, and then -4, and the last term, the constant of 8. All I did was use the coefficients, not the variable. And what you'll see with the arrows is I just took that first number 2 and I dropped it straight down below this line. So any number that's below the line, that 2, you multiply with that number on the left. 2 times 3 is 6. Notice then I put that in the second column. Now anytime you have a column of numbers, you add them together. -5 plus 6 is 1, and that drops it below that blue line. Now that that number is below the blue line, multiply it to the number on the outside. 1 times 3 is 3, and that goes in the next column. And we just keep repeating that process. 0 plus 3 is 3, drops that below. 3 times that 3 over there is 9, that goes to the next spot. -4 plus 9 is 5. The number goes below, multiply it to that number on the outside. 5 times 3 is 15, and look at this. 8 plus 15 is 23. That's the same answer that we got using direct substitution. The purpose behind this is both of these methods will always work as long as you follow the appropriate steps for each type of method. But synthetic substitution, we're actually going to use this synthetic method to help solve later in the chapter. That's why we introduce it now to show you kind of how it works, and we'll apply it later. Now in that second example down below, I'm just going to kind of get rid of some of this work right here. Notice when you're looking at the terms represented, we have 2 terms that we're missing. The x to the fourth term and the x cubed term. We had to have 2 zeros in our setup for that synthetic substitution. I plugged in -2 over on the left-hand side and then used all my coefficients. See if you can write this out on your own, kind of modeling that example up top, and try to get -127 as your answer. Finally, the last thing we talked about in the first part of the lesson was just naming types of functions. So far in math, we've talked a lot with linear functions and with quadratic functions. We wrote out their general or their standard form, and we talked about the lead coefficient and kind of what the shapes would look like. But once you get to higher ordered polynomials, the shapes can look kind of different. So take a look at a cubic function. A cubic function, kind of like a linear function, has arrows that go in opposite directions. So this said the shape was kind of like a roller coaster, which sounds really weird, I know, but the curve just kind of goes up and then down and then up, kind of like you're riding a roller coaster. A quartic function over on the right has a degree of 4. Like a quadratic function, quartics have arrows that go in the same direction, and it just depends if your a value is positive or negative. So we kind of say that a quartic function can look like W's or M's, but they can be distorted. They don't have to be really symmetrical. And then the last type of function that we talked about in this lesson was called a quintic function. Quintic has a degree of 5, which is odd, like the cubic function and the linear function. So notice the arrows go in opposite directions, and it always depends on what your lead coefficient is. So we call this a crazy roller coaster because it has more loops in it than a cubic function does. In the next part of the lesson, we talked about how to kind of figure out where those arrows go with what was called end behavior. So that'll be a second video that I send you.